Question number 84. It's a capacitor charging problem. A capacitor of capacitance C is given an initial charge of capital Q. At t is equal to 0, it's connected to an ideal battery of EMF E through a resistance R, and find the charge on the capacitance at time t. If you have not seen the capacitor charging derivation, you may want to check it on this channel. So basically, this problem is pretty much same as the derivation of the charge on the capacitor. We know that if there were no charge initially on this capacitor and it's connected through a resistor R on a battery E, then the charge Q is given by CE1 minus e to the power minus t by RC. But in this one there is one problem, and the problem is initially we have a charge Q here, capital Q here. Now, for example, if you put t equal to 0 in this equation, then this whole thing becomes e to the power 0, and 1 e to the power 0 is 1, so 1 minus 1 is 0. So if there is no initial charge, the graph of this the charge on this capacitor looks like this. Okay, but we have an initial charge something like this. So this possibly could be doing like this charge. Assuming this charge, because of this charge, the voltage on this capacitor is less than the battery voltage, it would start increasing. Or if the charge given is more than this battery voltage, then it could possibly start discharging or something like, finally reaching to the E voltage. So we can calculate, but before that, let's do solve this problem. And the solution is going to be pretty much same as the derivation of this charging on the capacitor, except that the initial conditions are different, which is at t equal to 0 we have a charge Q which is non-zero. So to derive this equation, we write this voltage of the battery is same as the voltage across this capacitor and the voltage across this resistor plus the voltage across this capacitor. So E is equal to IR plus voltage across this capacitor will be V is equal to Q by C. This is a simple starting equation in which we know that we need to solve it for Q. So I want everything in terms of Q. E is constant, the battery is not changing, the resistance is not changing, capacitor is not changing, but I is changing with time. But we want all the things in one variable, and we want to solve for Q. So we write I as dQ by dt. So this whole thing becomes R dQ by dt plus 1 by CQ. Now the trick is to separate the variable. Keep all Q, dQ and everything in Q in one side, and everything that is related to dt on other side. So we write here as E minus Q by C on this side and R dQ by dt side, and thereby we calculate all the Q terms. CE minus Q on this side, CR dQ by dt on this side. Now we can take dQ divided by C minus Q. Here C minus Q is there, and the whole dQ terms come on this side, and RC dt goes over there and divided by RC becomes dt by RC, and it comes over this side. And finally we take the minus on this side, so it becomes easier. This C minus Q becomes Q minus C, and we have minus sign here. So it's nothing but simplification and separation of Q and T. Now we can take an integral on the both sides, because we can integrate with respect to Q, we can integrate with respect to dt. RC is constant, so RC does not interfere in integrating DC. The integration of 1 upon Q minus C is log Q minus C to the base E. And integration of dt is T, which is minus T by RC, plus a constant log K, and that is where the whole new thing comes up. Okay, so before we move further, let's simplify it a little bit. This is log Q. Okay, now even what in the derivation of the formula for the original this formula, we assume that at t equal to 0, Q is equal to 0, and then that's how we found the value of the log K or K. But here the initial condition is at t is equal to 0, this Q is not 0, it is capital Q. So we write this initial condition in this equation, then we will get log Q minus CE is equal to, this thing becomes 0 and this thing becomes log K. So log K is capital Q minus CE, or K is equal to Q minus CE. This is the value of this constant which we substitute in this equation back. So this thing equation becomes log Q minus CE is equal to minus T by RC plus log capital Q minus CE. And then when we do that, we get, we take this term to the left hand side and divide it by capital Q minus CE, and then we remove the log and take e to the e to the power minus T by RC becomes on the right hand side. The Q minus CE divided by capital Q minus C, which comes to the right hand side, becomes this. And this is our charging equation, which we can simplify for Q as CE plus Q minus C multiplied by e to the power minus T by RC. If we want, we can bring this Q terms outside, Q into e to the power minus T by RC, and collect these two CE terms. So CE 1 minus e to the power minus CE 1 minus this thing, collect this term minus T by RC.